homework 10, page 154, do 17, 18, and 19 first. Each one of those, it says, prove that the derivative of this is something else. And by the end of the class, you should know exactly what I'm looking for that. You're not going to plug it into a difference quotient. You're going to use, the difference equation. You're going to use the quotient rule for each one of those. I'll have an example of what I'm looking for, hopefully by the end of today. But then once you do those, you go back and do the rest of these, and then if any, I don't think anything from this, but from then on, you could just use what you've proved here, and that should make sense when you do it. So, okay. In case you couldn't tell by the extra stuff I assigned you, we're going to be taking derivatives of trig functions. Okay, so let's just jump right into that and think about this. Let's think about sine x. Now what we want is the derivative of it. That's what we're going to do today. We're going to take the derivative of it. But before we do that, let's just see if we could use a little bit of reasoning here. So here's sine x. It looks something like this, right? It goes through here at pi, has a max here at pi over 2, min at 3 pi over 2, and comes back to 0 at 2 pi. Now, let's just get a few points. So let's say that we want to take the derivative of this, and forget that it's sine right now. We're just taking the derivative of this function right here. 1 second, let me try to do this well. So remember, the derivative is just the value of the slope at a given point. There are a couple places here where we could easily figure out what it should be. So what would the value of the slope be right here?
0.
It should be 0. So the derivative should be 0 right here. Where else should it be 0?
3 pi over 2.
At 3 pi over 2, the derivative should be 0. So whatever this thing does, whatever it looks like, it should go through here, it should go through here. Now, I haven't drawn this very well, but if we could get in there and stuff and figure out kind of what the slope is right here, you could count some squares on Desmos and figure out that it's pretty close to about 1, it looks like. At any rate, it's a positive number, and so if I'm not trying to be exact, I could just say, okay, it's some positive number right here. Okay. What about here?
Negative 1.
It should be, yeah, and just by symmetry, you could tell that whatever this is, it's just the negative of whatever that slope is. If the slope is 10 here, then it should be negative 10, right?
Yeah.
And so whatever this value is, it should be that far down right here at pi. So let me try to see what's going on here. It looks like that. Now another cool thing about this periodic function is that whatever the slope is here, it's got to be the same thing here, because this is just a repeat over and over and over again. So whatever that value was, maybe it was 10, maybe it was 2, maybe it's 1, it's 1. It's got to be the same thing here. Okay. Now, I don't think that it looks like this, right? It's probably curvy, and you could see that by this is a nice smooth curve, right? When I'm thinking about tracing the slope, it starts at say 1 and slowly goes down to 0 and keeps going down and stuff like that. So maybe I'll connect it with some smooth curves and stuff like this. And so that was my next question, is what if you had to guess? You would guess that this function right here is what?
Cosine of x.
It looks like cosine x. So it looks like the derivative of sine x is simply cosine x.
That would be nice.
It turns out to be true. We're going to prove that today. But we're going to need to do we're going to do a lot of work for that, okay? And so, to actually prove it. Most books don't bother to actually prove it. They get to a point and then say, this is 1, and this is 0, obviously. And so, yeah, we're gonna do it rigorously today. But this turns out to be true, and okay, but just by definition, how do I get the derivative of something? What would I How do I do this?
As
It's the limit
h goes to 0.
of.
F of x
Sine.
plus
So that f of x would be
Sine x plus
sine x
Plus
plus
h.
h. Not sine x plus h, it's sine x plus h. Okay.
minus sine x.
Minus sine x
over h.
all over h. Okay. Now what do you do?
Yeah.
Yeah, that's a good question. Don't we have some kind of rule
Oh, yeah, yeah.
for when we
Oh, yeah,
have...
it's like-
let's think. Sine of a plus b is...
It's like would be sine x
Sine-
times cosine.
It's... Yeah, and remember, so
Sine
this is the one that goes sine
cosine.
cos... Sine cos...
AB.
And the sign is the same.
Yeah.
With sine, the sign is the same. And so, okay, since that's the case, I'm just going to go ahead and do this and say, okay, limit. And I have no idea, as of right now, whether or not that's going to help me, but right here, like, what do you do with that, right? What the heck? So, the only thing I know how to do to make that expression look any different is to go ahead and use what we just said, the whatever formula? Addition, whatever it was, yeah. So it goes sine cos plus sine cos. And now I'm going to put that minus sine x in here. This is still all over h. And now, what do we do? It's the x
X.
first, then h. So
And an h.
x, h. Then it's the other way around, h, x. Okay, now what do you want to do?
Could do that weird thing where you add and subtract.
You could, and it won't help. In this case, one thing I notice right away is I have a sine x right here, and I have a sine x right here. Maybe if I get them together,
We could factor out.
maybe, yeah, maybe. And thinking this is not a limit as x goes somewhere. This is a limit as h goes somewhere. And so if I could isolate those x's, those are pretty much constants, right? And so that's kind of what's going through my head here is, as far as this limit is concerned, this is a constant number. This and this, which happens to factor out of there, is a constant number. And so really if I could isolate this so that I could get a limit of something with just h in it, maybe that'll make my life easier. I don't know yet. Maybe it will, maybe it won't. But as I'm flopping around gasping for air, I'm just going to try it. I'm going to say, okay, what happens if I just isolate the h parts, isolate the x parts? I'm going to go ahead and write it this way. Now this is all over h, or like this as well, right? Right, that's the same thing. And now I could kind of see, like you could think about this as two limits. And as far as cosine is concerned, he's just a constant. As far as sine is concerned, he's just a constant. And so I could take the limit of this part, as h goes to 0, and I'm just going to worry about the h part and say that constant x, he could just come out. That sign is not going to change as I change the h. So he's a constant. I can just pull him out, right?
Yeah.
No problems there. I could take the limit of this, ditto with that. Cosine is just right there. Cosine x, limit, as h goes to 0 of sine h
Wait, we just
over h.
figured these out.
And these are the two limits I told you guys. I was like, I want you to evaluate what are these limits. And what did you get?
0 for
zero
the
and
cosine
one.
one.
You got 0 for this one.
And
And
1
1
for the other.
Okay, so that would be sine x times 0, if indeed that limit does go to 0, which I think it does. And this right here, you said that this limit goes to what?
To 1.
Yep, that's what you should have gotten. That's what I wanted you guys to do. So, as far as I'm concerned right now, and so, okay, sine x times 0 is what?
0.
And cosine x times 1 is what?
Cosine.
And so, indeed, it all hinges on this. If this limit does indeed go to 1, and this limit does indeed go to 0, then, as we expected from the beginning, this should equal cosine x. But now we have some work to do. We need to show that this limit is indeed 1 and that this limit is indeed 0. That's what we're going to be doing for the rest of the day. This is not easy. This is not easy at all. I want to do it rigorously because you're never going to see a rigorous proof of this. And in fact, I'm going to kind of half do it rigorously, as you'll see. I'm going to kind of fudge half of it, but it's going to be worth it, okay? So, I'm curious. So I want you guys to remember this, okay? This is how we got here. Now, the only thing we need to do today really are these two limits, okay? So, remember, the derivative of sine is cosine just as long as we could show that these two things are true. So, I'm going to put those up there because that's our goal for today. We want to show these two things. We want to show, I'm going to write this one first. We're going to show that the limit as h goes to 0 of sine h over h is equal to 1. That's one thing we need to prove. The other thing we need to prove is that the limit as h goes to 0 of cosine h minus 1 over h is equal to 0. Okay, I'm curious. How did you guys, is this what you guys got for these?
Yeah.
How did you figure that out?
I plugged in points.
Plugged in numbers, right? So you could just plug in like sine of 0.01
Yeah.
over 0.01 and you see that it's like 0.99 something. You plug in sine 0.001, right, over 0.001 and you get like, I don't know, 0.999.
Also graph.
Okay, yeah, good. I want to go there too. So you could also do that with the negatives. You do it with negative numbers and you see like, yeah, in both cases, they're both getting closer to 1.
Yeah.
Right? It does if you don't believe me.
Yeah.
You could do the same thing here, plug in things very close to 0, so the positive and the negatives of the 0.01s and stuff, and you'll see that the value gets closer and closer to 0. Another way you could do it, and this would be the first thing that I would do, is just go to Desmos and graph sine x over x. And you'll see that that graph looks something like this. And in both cases, as you get closer and closer to 0, this value gets closer and closer to 1. You could graph cosine x minus 1 over x, and the thing that you get looks like this. And you can see that as you go to 0, in both cases, the values get closer and closer to 0. And so you could deduce, and this is what you did. You deduced that, yep, this guy goes to 1. This limit should be 0, right? Okay. So what we're going to do is prove these two statements rigorously. But in order to do that, we need the definition, and in order to actually prove it, we need to have some idea of where it's going. Right? If we didn't know, right, and we're just trying to find the limit of sine h over h, and we don't know what it is, then we're trying to prove some statement like this, minus L less than epsilon, and it's like, well, what's L? Yeah. And so in order to do something like this, we need to know where we want to start, right? And so to do what we're about to do is kind of necessary. So, okay, I have a little spiel I want to say before we do all of this. Okay? This is how we're going to prove these two statements. In fact, let's go ahead and write down what we need to prove for this. So, rigorously, what does this mean? It starts with a for all.
Oh, for all epsilon bigger than 0.
For all epsilon bigger than 0. So you give me any number, any positive number.
There exists a delta also
another positive number such that
0 is less than 8.
Yeah, and I'm not going to worry about that side for right now, but h
minus
where's it going?
0. Yeah,
Right. The distance from h to 0
is less than
when the distance from h to 0 is less than delta, then right, which is
sine of h
sine h over h
minus 1.
1.
1 is less than epsilon.
That's what we need to prove. Okay?
Yeah.
This is what we need to prove. Here's how we're going to do it. First, we're going to make a geometric argument with a triangle. In fact, I'm going to write this down so you guys see. This is because there's going to be a lot of crazy stuff going on, and I want you to see. I'm going to tell you what I'm going to tell you, then I'm going to tell it to you, and then I'll tell you what I told you. This is a teaching tool, right? This is actually a good way to teach things. I'm going to tell you what I'm going to tell you. We're going to make a geometric argument, right, with a picture. And what that's going to give us is a bunch of inequalities that we want. Because obviously we're trying to prove something that involves inequalities here. And there will be very useful ones that will help us to do this. Okay? Then, after we make that geometric argument, we're going to monkey around with this guy right here. That guy. We're going to monkey around with it. And that's a technical term, monkey around with an expression. One monkeys around with an expression, okay? Until we get something like, okay, we have some stuff, and that's going to be less than, if we could get it, so that we could get, like, say, it won't be exactly this, but if we could get something less than h, the cool thing about this is we can make h as small as we want, right? Because really, this h minus 0 is just saying the absolute value of h. And if we can make h as small as we want, we could certainly make it less than epsilon, right? And that's the idea, right? We're trying to prove if this, then that. We don't know what delta is, but we have to discover what delta is going to give us this, right? And so we're going to monkey around with this until we get something like this and then say, whenever h is less than epsilon, that would serve as our delta. It's actually going to end up being 2 epsilon. But anyway, like, that's the idea behind what we're going to do here. I'm going to monkey around with this until we find something like, oh, look at that. We can make h as small as we want. H is smaller than epsilon, so just take it to be as small as you want. You know what I'm saying? Does that make sense, what I'm saying here? Does that make sense? Okay. So that's what we're going to do. We're going to monkey around until we can say, oh, look at that. I can make that smaller than that because it could be arbitrarily small or sufficiently small, right? Okay. And then and we're going to burn through this, do it in reverse. Because we're trying to prove if this, then that. In order to do that, we're going to need to take this apart and find one of these. But then we want to make sure that, okay, we found our delta. Does this indeed imply that this is true? And so we're going to do all of this work from number 2 in reverse. And I'm going to burn through that really quickly. But just to make sure that, yes, we do get, I found my delta. You give me an epsilon. I'll find my delta. And that delta, whenever h is smaller than it, does imply that this thing gets arbitrarily close to 1. Everybody with me on that? Okay, so here we go. Part 1, the geometric argument. And I'm going to go ahead, I'm going to get rid of this. We'll come back to that. Okay, so here's the geometric argument. Oh man. Now your book does something similar. I have not taken a look at how the book does it. This is Justin's proof here. And I did that delivery. I did not want to see how the book did it because it's something you're going to see all year. I'm not going to look at how the book does it. That way, if I do it differently, then you have 2 points of view on, which is cool because if one doesn't quite make sense to you, maybe the other one will. This is something I like to do deliberately. But from just glancing at what the book does, it's not the same thing. So that's cool. Let's take a line segment and let's say that this line segment has length 1 from here to here. Okay? Everybody with me? Okay. Now, we're going to pretend that this is the radius of a circle. And we're going to draw out the arc of that circle like this. Okay? Everybody with me?
Yeah.
Okay. So what's this length right here?
1.
It's still 1. Okay, that's still 1. Now, how far did I go? Well, this is going to be the first thing I'm going to do. I'm going to suppose that h is a positive number, but it's also a small positive number. We don't really need to do that. Any positive number will work, but the drawing I'm about to do will get weird if it's bigger than 2 pi, because, like, obviously. So I'm imagining that h is small. What is h? Well, h is going to be the number of radians, right there. Okay?
Yeah.
Okay? And obviously, you can see why I'm doing this, because we're letting h get really, really small. We're going to figure out what happens as this gets really small. Okay? Now, I'm just going to say right away, we're only going to do the positive case here. We could spend another 30 minutes doing the negative case. Okay? So really, what I'm going to do here, the things that we're going to prove, is the right-hand limit here. And then I'm going to make a really hand-wavy argument to say, like, it works when it's -2. So that's why I said we're going to do like half of a rigorous proof here. We're just going to do the positive case. The negative case, it's the same thing. It's just now the h is negative. When you multiply inequality, it flips the inequalities. And oh wait, that's now a negative value, and it's just a pain. So we're not going to bother with that. Is everybody okay with that?
Yeah.
Okay. Yeah, like, and you'll see, you'll believe this. Okay, I think this is sufficient. Okay, so that's what we have right here. Now, what I'm going to do is drop a vertical line right here. That gives me a perpendicular angle here and another perpendicular angle right there. Okay? Now, let's get some lengths here. I want this length right there. I'm going to call it x. I also want this height right here. I'm going to call that height y. Now, what do you think we could do? How could we find one of those?
Sine
Okay, sine of
h
is equal to
y
y over,
1
which is just,
y.
oh, nice. Oh, and the thing I'm working with has a sine h in it. Nice. Okay, so this height right here is indeed sine h, right? Okay, cool. There's sine h. By the same exact argument, you could say, okay, cosine h is x over 1, right? The adjacent over hypotenuse, which is just x. So that exact length there is indeed cosine h. Okay, nice. Let's get a couple more lengths here. Here's a tough one. What's the length of that arc? Does anybody remember arc length? Yeah, it's a tough one. So it's true, and this is the cool thing about doing things in radians, is that whatever, if you have some radius here, and you have a sector of a circle, that's what this is, a wedge that you cut out of a circle. You have a circle of radius r, you cut out a wedge from it, then the arc length right there, and if that angle is theta, the arc length is r times theta. It's like how we defined radians, remember? Because you have 2 pi is the circumference of a circle, and r, right, is 2 pi r, or wait, 2 pi r is the circumference, yeah, and so this is what it is. You take the radius times the angle in radians, and that's what that arc length is. So what is this arc length here? How do we find it?
It's h times 1.
H times 1, right? So the arc length, r theta, right, the radius times the angle, is just 1 times h, so that length itself is h. Everybody buy that?
Yeah.
Okay? Okay, all right. A couple more lengths we want. What's this length right here? What is?
Because
If that whole length
Oh,
is
the whole-
1,
so 1
And
minus
yeah.
cosine h.
there you go. This right
Yeah.
here, this length from there to there, is 1 minus
Which is
cosine
just
h.
sine. Wait,
No.
no, if we square
Nope. Nope, nope, nope. So, that and that. Now, here's another thing we could get. We want 2 more lengths here. One of the lengths that we want is from here to here. And if you notice, that is the hypotenuse of a right triangle. One of them is 1 minus cosine, the other one is sine. So how do we find that length right there?
Sine squared plus 1 minus cosine.
Plus 1 minus cosine squared, and we take the square root. right?
Yeah.
It's the square root of that. That's just Pythagorean theorem, right? That squared plus that squared equals that squared, so its actual length is the square root. Now let's clean this up a little bit. So real quick, let me get some room here. Let's multiply it out, okay? So we have sine squared plus, what happens when I multiply that out?
1 minus 2 cosine
1 minus 2 cosine
plus cosine squared.
plus cosine squared. Now, sine and cosine, put those
So
together.
it's just 1.
Right, so sine squared plus, I just want to have this all written out to make sure I don't mess anything up. That's 1, sine plus that. So that's 1 plus 1 minus 2 cosine.
So then
So that's
2 minus
2 minus 2 cosine. Ox, O-C-O-S. Now, we could leave it there, but what's going to help us later is if I write this as 2 times 1 minus cosine h. Like that. Everybody buy that?
Yeah.
That's the length of this guy right here. So I'm going to write it like this. 2 times 1 minus cosine h. Like that. All in that root. Right? Okay. All right. Now there's one more length that we're going to need. And it's this total length that you'd get if you walked straight across here and all the way down here.
It's just sine h plus 1 minus.
What? Wait. It's what?
Sine h plus 1 minus. cosine
Yes,
h.
exactly. Right. So sine h for this part. So this entire length is going to be sine h plus that length right there, which is 1 minus cosine h. Okay, so we have a total of 1, 2, 3, 4 lengths. And I would like to find out which is the shortest, which is the second shortest, which is the third, and which is the longest. Which of these 4 is the shortest?
Well, it looks like 1 minus cosine.
Well, we're not dealing with him yet. I don't care about him.
Oh.
Just
Oh, right,
these
you
4.
just-
1, 2, 3, and 4.
Sine h.
Sine h has got to be the shortest. Why? Well,
Yeah.
that's the hypotenuse of a triangle.
Yeah.
Obviously, it has to be longer than one of the legs. So, sine h,
It just goes in order.
and it looks like it, right? So sine h has to be the shortest. And we don't really, we don't really need this. But I'm going to say, right now, he's positive. Right?
Yeah.
Like, if h is not 0, I don't care how small this triangle is, that height right there is not 0. We don't really need that, but I'm going to use it. And so, whatever. Okay, so it's positive. And now, which is the next biggest?
Root 2 times 1 minus cosine.
2 times 1 minus cosine h. Okay, so everybody buy that.
Yeah.
Which is the next largest?
Sine h plus. Oh no, h. Sorry.
H itself. Now, here's the thing. Later on this year, we'll be able to prove that the shortest distance from between 2 points on a plane is indeed a straight line. We'll be able to prove that.
Isn't that all?
Yeah. That's
It should be.
Who said that?
Do you prove it?
I can't prove
Yeah, that's what I thought. Later on this year, we'll be able to. And so, but here's the thing, we're just going to take it as gospel truth, like, yes, okay, the shortest distance is there. Therefore, any other path that you took must be longer.
Yeah.
Okay, now, this looks like the longest possible path, right? Without going out of your way, right? Like, you go, here's a city block, here's another city block. The longest possible way would be if you walked all that way to that way, which we said was this right here, sine h,
Yeah.
plus 1 minus cosine h. Everybody buy that. So part 1 is done, okay? This is the first thing that we wanted. This inequality, or series of inequalities, however you want to think about it, will help us prove the statement that we want to prove, okay? So it's really important. I'm going to put it up here. I'll do it right here. 0 is less than sine h. and this is, we're assuming is for a positive. You see why this is a pain is because if when it's negative, when you're coming from the opposite side, this is a negative number. This is also a negative number. Now you're dealing with distances, and it's like, well, the distance itself is, then it's negative. And so it's just a pain because you have to just keep track of all this stuff and say, oh wait, yeah. And then when you divide by an h or multiply by an h, you have to remember, oh, that's a negative number, so it flips the inequalities. It's just a total pain, and I don't think we need to worry about it because what I'm about to do should be sufficient here, okay? So root 2 1 minus cosine h less than h itself, which is less than sine h plus 1 minus cosine h. Okay, everybody buy that?
Yeah.
Okay, cool. That's what we need to actually prove this. Now, let's see if I've missed anything here. Did I miss anything? Nope, nope, nope. Okay, so now, moving on to part 2, I said we're going to monkey around with the epsilon inequality. That was sine h over h minus 1 less than epsilon. So we're imagining somebody gave me a epsilon, and I'm trying to show that this is true, and I know that I can make h as small as I possibly want. Why? Well, because h is going to 0, and so he's going to get smaller and smaller. And so if I make this really small, as you've already seen, when you plug in small numbers, it does get really close to 1. Like you could do this with a calculator and say, oh yeah, indeed, if epsilon were, say, 0.01, I'm sure you could just keep plugging in h's until this gets small enough, right? Okay, so now we just need to do it rigorously. So how do we get out of absolute value? What does this mean? Because right now I'm just monkeying. I have no idea where I'm going yet.
So it's minus epsilon in it.
There you go. That's all that means. That is what that absolute value means right there. There's no difference between this statement and that statement. They mean the exact same thing. So now, I don't know. I have a nice inequality that involves h's and sines. Maybe if I try to isolate them, I don't know. So I'll just add 1 here. I get 1 minus epsilon sine h over h less than 1 plus epsilon. Everybody with me on that?
Yeah.
Here's the great thing, because I chose a positive value for h, I'm going to multiply through by h, and I don't have to worry about flipping anything around, right? And so I'm just being lazy here, and sorry, but multiply through by h, and now what we have is h minus h times epsilon, right? Or h times 1 minus epsilon, but I went ahead and just, distributed it out. Distributed it out. Everybody buy this?
H plus h epsilon.
H times epsilon. Right? I haven't done anything crazy here?
Yeah.
Now, 1/2 of this is pretty much done, because check this out. Sine h is less than h. Right? Right? That's what that means?
Yeah.
And so it must also be less than h plus any other positive number that you gave me. Since we assumed that h is positive, and we assume that you have a positive epsilon, then h times epsilon is bigger than 0 also. Yeah? So, there's my positive number. That was easy. That's half of it right there. Okay? You buy that? Okay. Half done. Here's the hard part. Well, what about that guy? Yikes. Well, I don't really know. I just play around with it. Okay, maybe. Okay, so what we're trying to show is that this is true. That's what we want to show. If I make h small enough. Now, on the other hand, it doesn't matter what h is. It's always going to be true as long as h is some positive number. That's cool. What about this? Can I show that that's true? Well, yeah, good luck. Maybe I'll monkey around with this a little bit, and I'll get h. Maybe I'll take the sine over to this side. So h minus sine h. And I'll bring this guy over, h epsilon. Now here's the question, can I show that this is true? Well, I don't know, but I know, again, because remember what I'm thinking about here is I need to find a delta. I'm going to monkey around with this, and then hopefully I can work my way back, right? And so let's just see here. Let's look at this inequality. And I could get an h minus sign, because here's my h. If I subtract a sign from all of these, let's see what happens. In fact, I'm just going to start with this right here. Since sine h is less than h, which is less than sine h plus 1 minus cosine h, you guys buy that?
Yeah.
I just left him out because I don't need him right now. But now if I subtract sine from each one of these, subtract off a sine and I get a 0. Subtract off a sine and I get a h minus sine. Subtract off a sine, and he's not there anymore, I just have 1 minus cosine h. Everybody buy that?
Yeah.
Okay, so that's true. Like, we're trying to show that this is true. We don't know whether or not this is true yet. We know that this is true, because we went and derived this. This follows directly from it. This must be true. So now the question is, if I could, so we already know that this value that I care about is less than this. Maybe if I could show that this is less than this, maybe that'll work. And one place up here in the stuff that I already know is true, I already know that each one of these statements is true, is that I have a 1 minus cosine. He's living right there. So maybe I'll just monkey with that, and we'll see. Because remember the goal here. So first off, there's h. Okay, so that's true. We know it's true. We showed that geometrically. And now it's like, maybe I could just isolate this and see what happens.
Just square both sides.
We'll square both sides. That gives me 2 times 1 minus cosine h.
Divide by 2.
H squared. And this is a nice thing, because h is not negative. We don't need to worry about, well, but then if it's negative, it's... And so, yeah. Okay? Divide by 2, and we get that 1 minus cosine h, h squared, is less than h squared over 2. Now I'm starting to see, wait a second. I need to show that this is less than that. I've shown that this is less than that, and that that is less than this. And so now it's just a question of, can I show that this indeed is less than h times epsilon? Let's just see. Let's see what happens. And so maybe I'll divide both sides by h. Again, h is positive, so I don't need to worry about it. That's cool. H over 2 is less than epsilon. Oh, here it is. So whenever h is less, so let's think about this now. Whenever h is less than 2 epsilon, there's your, oh, we don't have it up there anymore. There's your delta. In other words, if you let delta equal to epsilon, then whenever h is less than it, then it will be the case that h over 2 is less than epsilon, and that h squared over 2 is less than h epsilon. H squared over 2 we've shown is bigger than that, which is bigger than that, and therefore, right, so here, putting it all together here, what we have is that when h is less than 2 epsilon, then h minus sine h is less than 1 minus cosine h, which is less than h squared over 2, which is indeed less than h epsilon. And that's what we want. That is exactly what we want right there. Because now, if h minus sine h is less than h epsilon, then h minus h epsilon is less than sine h, which gives us the other side of that inequality that we wanted. Because we've already shown that it's less than h plus h epsilon, and so it is indeed bounded, which means boom, 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 we get it. That's cool. Okay, so now I'm gonna work backwards really quick, just to make sure that it all adds up. Probably shouldn't have erased all that. Oh well. Okay, so, oh man, try to do this quick. We're going to pretend we didn't erase all that stuff that we had. So, let epsilon be given. Okay, so you gave me some number, 0.0001. I said, okay then. Then take delta equal to 2 epsilon. So when h is less than delta, right? And the absolute value of h is less than delta, then h is less than 2 epsilon, right? Okay, so that h over 2 is less than epsilon, so that h squared over 2 is less than h epsilon. Yeah?
Yeah.
Okay, that's one thing we need right there. Also, we could say, since this is true, then h minus sine h is less than 1 minus cosine h. Yeah? I just took this thing that we knew was true, subtracted off the sign from this guy and this guy and this guy. Well, I guess you know what I'm saying, right? That guy right there. I just subtracted off a sign from both sides. Okay, so that's true. And since this part then we have 2 times 1 minus cosine h less than h squared. So that 1 minus cosine h is less than h squared over 2, which we already showed is less than h epsilon. Yeah?
Yeah.
So h minus sine h is less than h epsilon, so that h minus h epsilon is less than sine h. Right? So since h minus h epsilon is less than sine h, and we know that that is less than h, right? Sine h is less than h. Also less than h epsilon. Yeah? Now, here's the last. Sorry, this got all everywhere. Now, I'll divide through by h to give me my 1 minus epsilon. Sine h over h less than 1 plus epsilon. Subtract off my 1, and I get minus epsilon sine h over h minus 1. Did I do that right?
Yeah.
Subtract 1 from everybody, and you get that. But that's exactly what this means. Sine h over h minus 1 less than epsilon. And so by definition, the limit as h goes to 0 from above of sine h over h is equal to 1. That is what we wanted to show. So, this part, proved. Boom! We got it. Yeah. You will never see that anywhere. Yeah. Okay, alright, so we got one of them down. Woo! Alright, the next one, believe it or not, is actually easier. So we're almost there, right? Because we need both of those to be true for sine, for the derivative of sine to be cosine. Okay? And I'm just going to burn through this because this one is not that bad. So let's think about the definition of this. This means for all epsilon, there exists a delta such that whenever the absolute value of h minus 0 is less than delta, then it's true that cosine h minus 1 over h minus 0 is less than epsilon.
Yeah.
But that's really easy to take care of. So as we're monkeying around with this is just cosine h minus 1 over h. Minus 0 doesn't mean anything, really. And so, okay, minus epsilon less than cosine h minus 1 over h less than epsilon. You know, we had some interesting stuff going on with that 1 minus cosine last time. Here we have cosine minus 1.
Factor in negative.
Yeah, and so let me just clean this up a little bit. We have minus h epsilon Because let's just pretend that I'm just in, right now, I'm just in plug and play mode. Like I'm just messing with equations to see if anything now. Ooh. Hey, look, we have a 1 minus. And in fact, didn't we just show? In fact, wasn't that one of the things that we showed? That 1 minus cosine was less than h epsilon? Like that was the thing. It was less than h squared over 2, which we said that's less than h epsilon whenever h is really small. Huh. So let's multiply everybody through by -1. -1 times negative h epsilon, that flips this guy. -1 times cosine minus 1 bigger than -1 times h epsilon, which is positive h epsilon is bigger than 1 minus cosine, which is bigger than negative h epsilon. Or how about negative h epsilon is less than 1 minus cosine h less than h epsilon. Right? I just rewrote it that way.
Yeah.
Because that's the way my brain thinks about it. Is on the left you're less than, on the right you're greater than. And so, in other words, if we could show that this is true for some value of h, then we get this, 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 which is what we want to show. Okay? And so now, the same thing, we just did this. We know that, so let epsilon be given. So you gave me some number, 0.001. I'm going to say, then let delta equal 2 epsilon. And just like last time, I'm not going to go through it all, but we could say, then h squared over 2 is less than h epsilon. And we already saw that h squared over 2 was indeed bigger than the 1 minus cosine h. So we got that half of it done. That half's super easy because I'm kind of cheating here. Like, well, actually, ooh, yeah, no. So check this out. So we have that part done. This part, check. Done. Now the other part comes from this. We have sine h less than sine h plus 1 minus cosine h. Right, I'm just using that one and this one here, right? That's less than that. That's less than that. So I'm going to subtract sine from both sides. And so that's bigger than a negative number, isn't it?
Yeah.
Okay, we got it. 1 minus cosine h is bigger than minus h epsilon. But it's also smaller than h times epsilon whenever h is less than 2 epsilon. Yeah. Okay, that's what then we just work our way backwards and say, boom, there it is. So, therefore, this is true. Everybody got it? All right. Okay. So, okay, do you believe me? Do you believe it? Like, have we done this?
Yes.
We've proven this rigorously. We use the rigorous definition of a limit to prove these two limits right here. Okay? And so now, just like we said before, the derivative of sine x is, we ended up with, it was sine x times this limit plus cosine x times this limit h, yeah, and we just said this guy goes to 0, this guy goes to 1, and so the derivative of sine x is cosine x. Boom! Alright, now let's do cosine.
What was like the hand wavy argument for that?
Well, just like, well, when h is negative, because you see, we've only proven from the right-hand side.
Yeah.
So I'm just kind of saying, and one way you could hand wave is to say, this picture that I drew, all the lengths stay the same if h is negative, it's just that when h is negative, you come down here. when h is a negative number, now you measure down.
Yeah.
Right? And so now this, technically, this sine h is now a negative number. This is still a length, that's still a length, that's still a length. And so it's kind of a, you just have to be careful, but you could piece it together the same way. And then remember, like, we ended up with stuff like this, sine h over h less than stuff, and then we multiplied by h. Well, when you do that with a negative number, it reverses the signs. So it's just a pain, right? So I'm just hand waving and saying, trust me, it works. If you were so inclined, I bet you could piece it together. But I don't want to waste our time. So, everybody got it?
Yeah.
All right. The derivative of cosine x is equal to the limit as
H
H goes to 0 of cosine of x plus h minus cosine of x all over h.
What do you think I'm going to do with cosine?
Do the thing, or this addition formula.
Addition formula.
Yeah.
And so cosine doesn't go sine cos, sine cos. It goes cos sine sine. Okay, so we have cos sine sine. And what about the sign in between?
It's minus.
It's different. Sine is the same, cosine is the opposite. And so xh minus cosine. I'm going to do the exact same thing we just did and say, let's try to get all the cosine x's together. You kind of see what's about to happen. The limit as h goes to 0. Cosine x, cosine h minus cosine x. There's a minus sign here. There's a minus sign there. That's a minus sign. That's a minus sign. Okay. I have to say, because it's so easy to mess that up. Everybody buy that numerator is good?
Yes.
Everybody buy that I could split that denominator like that. Okay. That's a minus sign.
Yeah. So.
Okay. Just making sure. Now I could factor out a cosine. And since it's x and not h, I don't care. I can factor them out of the entire limit. That leaves me cosine h minus 1 over h. Oh, cool.
Oh.
This is a minus sign. This is a minus sign. That's a minus. Okay? I could factor out my sign. Limit as h goes to 0 of sine h over h, which...
Well, it's nice we already.
It's nice that we already proved those. And so, this guy goes to
0.
0. He's gone. This guy goes to...
Sine x.
So it's negative.
This guy goes to
1. So
1. And so
Negative
1. And so it's negative sine x. That's why I said negative like 1,000 times, because this will mess you up. Sine goes to cosine, cosine goes to negative sine. And let's just real quick, let's just see, I'm going to just draw cosine. Okay, cosine starts here, comes down, goes up, and so its derivative would start at 0, but then become a negative number.
yeah.
Negative until it gets down to here where he comes back up to 0. So he's negative, he gets more negative, and starts getting less negative and comes up like that.
Yeah.
Here he's at 0, now he's positive the whole time. He's positive, gets more positive, then starts getting less positive, till he gets back to 0. So he does something like this. And so its sign, it's just been negatived. Right? We took the sine values and we made them negative. This is negative sine x. Okay, all right. Now that we have these, we could do all of the trig functions.
Yeah.
Now, 17, 18, and 19 will have you do it for cosecant, secant, and cotangent. So let's do tangent together. And this is what you should do. It'll say, okay, prove that d dx of tan x is something. And this is what you need to do.
Division.
Yeah, we're going to say, okay, then the derivative of tangent is the same thing as derivative of sine over cosine. Now, what rule do we use here?
The division. Quotient.
Quotient rule. So that is, and I'm just going to do it like this. I'm going to say, you take the derivative of the first, multiply, leave the second alone. Subtract, leave the top alone, take the derivative of the bottom. Divided by cosine squared. So now, okay, so now we have, so what is the derivative of sine?
Cosine x
So we have cosine times cosine
minus
sine times, yeah, cosine goes to negative sine.
plus, oh, so it's 1.
That's 1 on the top, and so that's cosine squared plus sine squared over cosine squared,
1 over.
which is 1 over cosine squared, which is secant squared x. And you see, this is, as you do this, you might end up with sines and cosines, but it will tell, like, these will tell you, prove that this equals that. Well, then that's just what you need to do, right? And so it'll say, like, prove that the derivative of cosecant is negative cosecant x times cotangent x. And negative cosecant times cotangent is the same thing as negative 1 over sine times cosine over sine. So I'm willing to bet that as you do this, you're going to get there to the bottom and you're going to have negative cosine over sine squared. And then, well, you're not done because it told you to prove that this is true. So you just take the next step. You go, well, negative 1 over sine times cosine over sine is the same thing as negative cosecant times cotangent. And then you're done, right? And that's the thing about these. We also could have written this like this. This, like, what if we would have said, ooh, look at this. That's the same as cosine squared over cosine squared plus sine squared over cosine squared. Well, that's the same thing as 1 plus tan squared. Well, yeah, because 1 plus tangent squared is the same thing as secant squared. So that could cause some consternation, right? You get here and you're like, all right, and then you check the back of the book and it says this, and you're like, how did that happen? And you just got to remember, like, that's trig functions, man. They do that, and so you got to be careful. So you do 17, 18, and 19 like this, and then the rest of these, it's gonna you just do this. You could. I don't think that there are any that utilize 17, 18, and 19, but if there are. There are. 11 will have, and 7 will have them. You could just use them. What I'm saying is, like, so for instance, 11 tells you to find the derivative of, it gives you f of x. Number 11 says secant x over 1 plus secant x. You could change all of these into sines and cosines and do it that way. Or you could utilize the result that you got here to do this. And let's just think about this. This is a quotient, so you'll need the quotient rule, right? Though it may be easier to do it with sines and cosines. I don't know. It's up to you. This is for you to figure out. So, any questions? All right. I can't believe we got through it.
Yeah, we made good time.
And wow, it's only 12:30. Actually, so what was that problem that you had? It was, you said 71?
I think it was the
was
tangent line one.
Tangent line.
Where it all goes through one, like, find 2 tangent lines of x squared.
go
that
through-
Show that there are
Negative
2
1, right?
tangent lines to x squared that go through 0, negative 4. Okay, that's...
Negative.
So if you're not drawing a picture, you're going to have a rough time. So we want to show that there are 2 tangent lines to this function that go through, so two tan lines that go through 0, -4. Okay, so first off, let's just draw x squared. Now it's saying that there should be two tangent lines that go through this point right here. So one of them must look like this. Yeah. And the other one must look like this. Yeah. Right? So, okay. So then the question is, how do we do this? So, first off, let's see. This line has the form y equals mx minus 4. Right? mx plus b or mx minus 4. That slope has to be the same as whatever this is right here. I don't know what value this is. I'm going to give it a special name. Let's call it x0. So that I don't mess it up with a different x. There's only one point over here on the right-hand side, and so I'm going to call it x0. Okay. So f prime at x0 is going to be equal to m. Yeah? And when I plug in x0 into this line, it should give me the same thing as the actual value of the function itself. Yeah?
Yeah, okay.
Okay, so f of x0 has to be the same thing as when I plug it into here, which should be m x0 minus 4. So now we have two equations. F prime of x0, so f prime is just 2x. And so that would be 2x0 equals m. Okay. So if m equals, so there's one, 2x0 equals m. And we know that m, so I could plug this in right here. There's 2x0 times x0 minus 4. F of x0 is x0 squared. Yeah?
Yeah.
And so we have x0 squared equals 2x0 squared minus 4. So I'm going to bring the 4 over, subtract off one of these to give me just one of them like that. And so now take the square root and we get x0 is equal to plus or minus 2. And I'll bet you, the other one is this guy right here.
Yeah, it's just the
It's gotta be, right? And so there you go. Oftentimes, so there is gonna be, later on this year, not too far from now, when we do optimization, there is this wicked hard optimization problem. And I'm gonna make a big deal of it. It's gonna be like a project. It'll be like a weekend project for you guys because it's so stinking hard. And it comes down to, when you're doing stuff like this, recognizing, wait a minute, this has to be a point. It's not just x. Because if you didn't have that, right, you would, like, if we didn't do that and we just said, well, mx and this and that, recognizing that this is some actual value that you care about, it might actually have been easier to just call it a, because then we have a bunch of x zeros and x's and...
But then I messed something up. I think.
And so, like, you plug in an x, but there's an x in the other formula, and it's just messed up. So it's really nice to stop and say, wait a second, that's a constant. Let's not call it x. Let's call it something else. I called it x0. It probably would have been better to give it a completely different name altogether, like a. And yeah. And I have not given anything away with this one problem that you guys are going to struggle with. I struggled with it for months. It was bad. Well, I mean, I wasn't working on it for months. It was just like in the back of my head, like, I wonder what the answer to that guy is. And try it again, and you end up like, wait a minute. And I'm going to take a look at your work, and I'll bet you've done the same thing. Where it's like, wait, I plugged this in, and now it's, where did it go? And